What's up, everybody? Welcome to part 6 of this tutorial series on doing visual odometry with the KITTI Odometry dataset and with OpenCV and Python. So we finally made it. This will be the last actual instructional video. In the last video, we finally came up with our function to estimate the motion of the camera between two subsequent frames. And so in this video, all we need to do is just make a function which will wrap that up into a way of iterating through each frame of our data set and then combining all of our frame estimates of pose change in order to create a contiguous trajectory for the camera over time. So, and then there will be one more follow-up video with the results, since it takes a couple hours to do all every single frame. Obviously, we won't record all that, so we will have a follow-up to show the results that we get, but they'll be mostly in line with the results that you see in the main notebook of the repository. So, so far, just to recap, we went through, we made a handler class, we did stereo depth estimations, and then we used those depths to recreate the 3D positions of features that we found detected and described using SIFT, and then we reprojected the locations of those features into 3D space using our stereo depth estimates. We used those 3D reprojections in order to use the perspective endpoint algorithm handling outliers with ransack to estimate the pose change from the camera from one frame to the next. And now we can use those pose changes in each subsequent set of frames in order to do odometry with the camera and keep track of the trajectory over time. So for those people who watched the last video to the end, you might remember that I got a little hung up because I was a little surprised at the mismatch between the ground truth, which you can see here, and our first estimate of pose, which, as you might notice if you're very observant, is a little different this time than the last time I ran this notebook. And so I went through just to make sure that I hadn't done anything wrong in the demonstration, and I hadn't. Everything is right. What we're seeing here is just good old-fashioned error. And that error is coming from the fact that this process is not perfect. And it's because basically the entire backbone, the foundation of what we're using to estimate the pose change of the camera between these two subsequent frames is stereo depth recreation. And stereo depth is not perfect. It is an estimate, and so there's errors there. And so when we're reprojecting our features into 3D space using these stereo depth estimates, any error that we've introduced in that process is going to make our estimate of pose change slightly incorrect. And so I remember in the last video we figured out that in the first frame we were off by about a half a foot in the Z direction. So this is to be expected. And if I can open up this copy real quick, it'll take a minute to load. Should have had that. That's going to be sort of the downfall of the way that this has been set up so far, is that we're not correcting our estimates with anything. So the error will be accumulating over time from frame to frame. And as you can see, over time, the overall shape of the road you can see, where I think that the green line here is the ground truth, yeah, and then the orange line is our estimated trajectory that we're getting from our visual odometry here. And like I said, the shape of the road, you can see it, but obviously our estimate is drifting over time because we're accumulating this error frame by frame, and we're not correcting it with anything. Well, what do I mean by correcting? Well, when you're correcting, you would be doing something like a Kalman filter, where you would make an odometry pose estimate using your cameras, and then you would then do a correction step, probably by incorporating your LiDAR scan. And so it's a complex thing to do, and it's outside of the scope of this tutorial, but I may end up making a follow-up series where we try and do that, because essentially you would make a proposal for where the car is in this frame, and then you would take your LiDAR scan and establish what the likelihood of having that LiDAR scan would be based on your proposed position estimate. And then using that likelihood, you would then make an update step that would drag your pose estimate a little closer to what the pose would be most likely to be given your LiDAR scan. So that's a whole different bag of nuts, and I won't be able to go into that in this series. Obviously this has gotten long enough as it is. We're at 6 videos at this point, but I really, my goal here was to establish the architecture for visual odometry. Like what are all the ingredients? How is it done? And to demonstrate that using OpenCV in Python. And so we're not going to be doing any correction step now. We're just going to let the error accumulate and demonstrate the process. But so that's what we were seeing in the last video, is just this is just error that's being introduced from the imperfections of our process, and given the fact that we're not incorporating the LiDAR scan to correct this proposal or anything like that. And I even went in and when we did the disparity map, which we calculate the depth from, there are some parameters here which we did not experiment with modifying. So it's possible that a smaller block size may be more accurate, and I want to check that out now. So it's possible that that might reduce the error and give us better results, and the only way to tell would be to run some experiments. And so it's all here ready to be modified and played with. So I think that would be a good thing to do. Another thing that I went in and did right before I started filming here is I had these set to 3 instead of 1, and I went into the documentation here, and it says 8 times number of image channels times block size squared. And so I had that at 3 from like a different project I was doing where I was using RGB images, which have 3 image channels. And so in this particular case, we're using grayscale images, and so that only has 1 image channel. So I went in and modified this to 1 to see if, and that says block size squared too, so that's actually also not what I was expecting, because if you're going to use a block size of 11, then maybe I should go ahead and change this. Yeah, should be following the documentation here. I just noticed this just now. So yeah, I mean, these parameters are going to have slight effects. So let's actually restart the kernel, and you're watching it live here, folks. We're going to see if that adjustment makes a difference. Like I said, it says here in the documentation that the block size should be between 3 to 11, and it should be an odd number. So I'm using 11 because that's just what I had from before, but we could use any odd number between 3 and 11 and see what the difference in results might be. So I just changed that to not be the SAD window, but to the block size squared instead, which is what it should have been according to the documentation. So we'll see if that brings our estimate down here any closer to our ground truth. I'm not going to run that cell. Yep, and just give me just 1 second. We'll get down to the bottom here. And no. So this looks almost identical to what we had before. So clearly that didn't make a huge difference. But the point I was really just trying to drive home there is that tinkering with those parameters may reduce the error. But ultimately, if you were going to be doing this and hoping to correct for your drift and your error, you would need to be using a filter, a Kalman filter, particle filter, or some method of correcting your estimates using another sensor. And so in this data set, all you get is cameras and LiDAR data, and then they expect you to get creative with that. So my next step in my approach would be exactly what I summarized a minute ago, which is to create a proposal using visual odometry and then correct that proposal using your LiDAR scan somehow. And, there's literature on this. Another thing that you could do would be, instead of strictly looking at subsequent frames and then estimating the pose shift between one frame and its next frame, you could be incorporating a bigger buffer of frames there where, say, doing a 3D reconstruction in every frame, and then possibly trying to match the features between more frames, and averaging your 3D reconstructions to maybe mitigate randomized error in your stereo depth between frames to try and get closer to what the truth really is by using a little more data, and also by estimating pose between like 2 frames ago and the last frame, and then combining those estimates together again, because when you're averaging more things together, you tend to cancel out your errors, and you sort of, along the central limit theorem kind of thing, you get closer to what the truth is by ironing out the random error that you're generating in this process. So those are all things that could be looked at to try and mitigate this error issue. And there's literature on that. I intend to go after some of that myself. So again, maybe in a future video, or maybe a follow-up tutorial series, we can start getting real fancy with it. But as you can plainly tell from the 7 hours that we've been at this already, just establishing this skeletal architecture of getting our depth from our stereo, and doing everything that we've done here, I thought it was important to just try and get that architecture across, and then the fancier things of error correction come later. So all that being said, let's go ahead and finish this thing. So in the last video, we made our estimate motion function, which takes in our key points from our features that we're tracking in the 2 images, and then it uses the solve PNP ransack function from OpenCV to estimate the rotation and translation of the camera between those 2 frames. And since we can do this for every pair of subsequent frames, we can create a trajectory over time of our best estimate of how the camera moved frame by frame, and then line that up with our ground truth, which is the image I showed you over here. And if you had watched that last video to the end, I mentioned that really, because what the solve PNP ransack is doing is finding the origin of the camera's position in the last frame in the new camera's coordinate, or rather the new position of the camera, so the new coordinate frame. When we're tracking trajectory in most autonomous vehicle applications for experimentation, you're almost always going to be tracking the trajectory in the coordinate frame of the camera's first location. So this algorithm is actually sort of solving the reverse of what we're after, which is we want to know where the origin of the camera is going in with respect to the camera's coordinate frame when it starts, which is where we're setting our global coordinate origin, is where the camera starts right in the beginning. So for each pose estimate change that we get, we're going to want to relate that change back to the origin from where we started from. And that will be a lot more clear in a moment when we actually do it. But just going into this, I want to make that point so that nobody misses that, because that's very important. So we'll go ahead and make our wrapper function here, and we'll just call it visual odometry. This is it. This is the big finish line. It'll take in our handler class, whatever, you know, however we set that up. We'll allow ourselves to choose a detector, a matching type. In this case, we'll be using the brute force, even though we could be using the KD tree, the flan matching, which I went over in another video. We can set a filter match, match distance that we can use to do the ratio test to filter out non-distinct features, which I explained in detail in a different video. We're gonna set up what kind of stereo matcher we want to use. I'm gonna end up using the SGBM, even though we could use the BM and compare the difference. And this is another point where I'll direct you toward looking at the main repo notebook, because I do end up under each of these headers comparing a lot of different approaches, very slightly different approaches, with like stereo SGBM versus just changing different approaches, and then calculating the error and finding out which ones perform the best, and you know, which, and it turns out, and it's not surprising, that the SGBM gives slightly better results, because it's like a more complex algorithm. So, and then we'll be able to pass a mask if we want it. Depth type, I may not go into that. Yeah, let me give me just 1 second. Yeah, we don't need that parameter. Some of this is a little deprecated. We'll be able to pass a subset if we want to not run all 4,500 frames to make sure our function is working before we wait a couple hours. Yeah, I'm just going to close this up here. So, equals true. See, I might not need that either. Yeah, okay. Yeah, let's do that. I'm gonna set it to false for now. This is like something I added later, where you can do an interactive plot that, like I showed in the part 3.5, where you have an external matplotlib 3D plot that sort of shows the trajectory over time. That's what this will do, and so I'm going to include it, because why not, for the sake of fun. So, okay. I could have left some of this out, so bear with me, because the function in the notebook's it has a couple more bells and whistles that I don't know if I necessarily need to include here, which you can kind of tell from the way I'm deciding what to include and what not to include. But I think I'm just going to run with not trying to mess with it too much, so that I don't generate errors. So we'll include a line here that says determine if the handler has LiDAR data, because what I'm going to do with this is if the handler does have LiDAR data, then we can actually improve our depth maps by superseding any pixel coordinate that we are going to use a feature from, because our LiDAR is bound to be more accurate than our stereo depth estimations. So whatever the LiDAR says our depth is most likely going to be more accurate than any stereo depth that we would have generated for that pixel. So what this will do is whenever we come across a pixel location for which we have a LiDAR data for, we'll use the LiDAR depth instead of the stereo depth in order to try and reduce our error as much as possible. So yeah, we'll include some print statements here. So we'll report the methods being used to the user, and we'll say print generating disparities with stereo something, and we'll format that with string.upper stereo, yeah, matcher. So whatever we pass here, either SGBM or BM, this will report back which one it's using, so that the user knows for sure what the process is doing. And then we'll say detecting features with something and matching with something, and we'll format that string with string.upper, and this is just making the formatting look the way it actually does. The detector, and so if it's sift, it'll say capital sift here, and then matching with we'll be using brute force. Yeah. So, you can use F strings here if you prefer. For some reason, I kind of like using the format method on a string because it looks visually a little neater to me. But, captain's choice. And so let's say if filter match distance is not none, then we'll tell the user we're filtering feature matches at threshold of something times distance, and then format that with the, you guessed it, filter match distance. Right on. And then if LiDAR, we'll tell the user that we are improving stereo depth estimation with LiDAR data, which just seems like a smart thing to do. So we'll do it. And if subset is not none, then we will say that the number of frames is equal to whatever subset of frames we're deciding to use, and then else the num frames is equal to handler.num frames, which is going to represent the total number of frames in whatever sequence we loaded into our dataset handler. So if we do pass a subset, then this variable will be set to whatever number of frames that we're deciding to use. And that's just for, troubleshooting and that kind of thing. So you're not always running all 4,500 frames. So yeah, and we'll have a bit of fun with our plotting here. So if plot, then we'll make a figure. And this all harkens back to what happened in the part 3.5, which was a fun video where we did some fun with visualization. So I won't explain too much here because I explained it all in that video, but essentially what we're going to do is if we set plot to true, then as this visual odometry process is happening in every single frame, we will generate a external 3D matplotlib plot, and we'll update it on every frame to show us our developing trajectory estimates against our ground truth in black because why not? You know, you might as well have something to look at while you wait a few hours for this thing to do its thing. I don't know if it's a few hours, maybe just a couple hours. We'll see. So the view init that we settled on before was -20 elevation and azimuth of 270. And that's because of the intuitive way that a camera's coordinate frame is. If I'm a camera, then the z-axis positive goes straight ahead, x goes negative to the left, positive to the right, and y goes positive downward, negative upward. So this initial view angle on the axis will give us a perspective that is intuitive for the coordinate frame of a given camera. So essentially the coordinate frame of the car, because we're treating the camera's coordinate frame as the coordinate frame of the car. So we'll need a x's is the handler dot ground truth, where we get all of the frames, and then we want the first row, fourth column, because as we've gone over, the ground truth is 3x4 transformation matrices, where the first 3x3 part of the matrix is the rotation matrix, and the very far right hand column is the transformation, or rather translation vector. So if we want the x's for every single frame of the ground truth, then we'll say all frames, first row, fourth column, because that's where the x value of the translation vector will be found in every single frame. So for the y's, obviously it will be similar, except we'll need the next row, same column. Z's, handler dot ground truth, all frames, next row, same column. And we'll say ax dot set box aspect, and I talked about this in that video as well, where this basically makes sure that the x, y, and z axes are all on the same scale, so that the scale isn't distorted in any given direction, so it looks on scale with the real street that was driven, instead of some equalized, stretched out matplotlib interpretation of it. And then we'll go ahead and plot the ground truth that we just extracted from our handler class, and we'll make it black because that seems like a, you know, a ground truthy kind of color. Okay, so there's our if plot section where we establish our plot. And remember that if we're going to say that we want this kind of plotting to happen, we're going to want to be in matplotlib tk, because that's when you get an external matplotlib plot. This kind of technique won't work in the notebook style of plotting, so keep that in mind. So we're going to establish a homogeneous transformation matrix. I talked about this in the end of the last video, but just in case you missed it, the idea here is that the transformation matrices we've been talking about this whole time, which are what we're dealing with up here with the ground truth, which are 3x4 matrices, you can make them homogeneous by adding a row of zeros and a 1 on the bottom to make it a 4x4 matrix that essentially would be like an identity matrix, 4x4 identity matrix, with the 3x4 transformation matrix plugged into the top 3 rows. And the reason that you might do that is because it turns out that if you invert a homogeneous transformation matrix, then it will reverse the rotation and translation of the 3x4 transformation matrix that you put into it. So in this case, that will be useful to us because, as I just talked about before, our solve p and p ransack function we'll be solving our change in pose backwards. So if we want to get oriented in the changes that will all be in regards to the global coordinate frame, or aka the coordinate frame of the camera in the first frame, then we're going to need to be inverting each of these matrices that we solve for. And so this is why we're going to do this. So the first pose is identity. So yeah, that makes total sense, where in the very first frame, before the car has moved from its first position, because obviously its first position isn't going to be rotated or translated with relation to itself, then the transformation matrix is just going to be an identity matrix, because the rotation matrix will be an identity matrix, the translation vector will all be zeros, and then of course the fourth row will just be 0, 0, 0, 1, as it always is in a homogeneous transformation matrix. So it will be just a 4x4 identity matrix. So we also want to give ourselves a empty trajectory array that we're going to fill up with all of these pose estimates along the way. And so whatever our number of frames is will be the first dimension, and then it's going to be a 3-row by 4-column transformation matrix, which is the format that they give us the ground truth in, as I just mentioned up here. So this will be our catcher's mitt for all of our trajectory estimates for every single frame, whether that's every frame or our subset of frames that we have passed into this function. And so obviously the first trajectory is just going to be this identity matrix, except we only needed the first 3 rows because we're not going to be storing homogeneous transformation matrices. We're going to be storing 3x4 transformation matrices in line with the format of what the KITTI dataset would expect you to submit were you to submit your results to them. So we're going to go ahead and set up some mHeight and mWidth variables, just so we don't have to write handler every time. Okay, so we'll go ahead and decompose the left camera projection matrix to get the intrinsic K matrix, which we're going to need for our solve PNP ransack function. So we'll get K left, R left, T left, and we'll do that using the decompose projection matrix function that we made before. And all we need to do is decompose the handler.po, which is the projection matrix for the left camera. And the only real reason we need to do that is because we need this K left matrix here, because it's necessary to do the solve PNP ransack function that is at the heart of our visual odometry process that we're using here. So when we made the dataset handling class, we allowed the user to make a choice between whether or not they wanted to store all of the frames in memory, which could only be done if you had a lot of RAM. Like I have 64 gigs, so I could do that. But if you only have 16 gigs, or God forbid 8 gigs, then you wouldn't be able to possibly fit 4,500 stereo frames into memory. So, and for the most part, you literally don't need to, because we're dealing with these frames sequentially, so there is no reason to have all of those frames in memory simultaneously, because we're not like training a neural network here. We're doing a sequential process. So using generators is really the way to go. Frankly, the only reason I ever wrote it to store it in memory the first time was because I just wasn't thinking about it, because it fit in my memory, so I wasn't worried about it. But anyways, we're gonna make an if statement here that says if handler.lowMemory, then we're gonna tell the handler to reset frames, which will set all the generators back to the starting point. And then we're going to say that image plus 1, which image plus 1 will always be the next frame in the left camera, because we're going to have image left and image right, which in every frame we're going to be generating a stereo depth map. So we're making two comparisons of images in every frame. We're comparing the left and the right camera to get our depth map, and then we're also comparing the left camera now and the left camera in the next frame to get our estimated motion. And so first you get your stereo comparison from the left and right, and then you're going to be comparing the image left with image plus 1. And so what I'm doing here is saying that I'm setting image plus 1 to be, at the moment, the first left image of the sequence, which it won't be in just a moment when we start doing the for loop, because saying this once by itself here automatically puts our plus 1 pointer plus 1 from where our for loop is. So this is just a clever step to make sure that we're using this generator and storing this variable will always be the plus 1 image of the left camera. So we run it once here before the for loop starts in order to get the generator to be one step ahead of the generator for the right camera. So hope that makes sense. So okay, so now is our main for loop. So we will iterate through all frames of the sequence. So we say for I in range of the number of frames that we're doing minus 1. So it would be a huge bummer to get to the end of all of these frames and then run into an error, because it turns out that the generator can't generate a plus 1 image past the last frame of the sequence. So we want to only do a range of the number of frames minus 1, because if we don't have a subsequent frame to be estimating our trajectory into, we're going to hit an error, because the trajectory that we're estimating corresponds to image plus 1. So once image plus 1 is the last frame of the data set, then we can't go any further. So I mean, that's pretty clear. So I don't want to over explain these things, but then at the same time, this is pretty complicated. So I want to make sure that I'm explicit enough to not leave, any details out that are important. So I think I've imported date time already. Yes. Okay. So we're going to time each of these frames as we go through, because we want to know how long it's taking so that we can make comparisons, and also sort of make a proof of concept, which is that this will not run in real time, because the frame rate of our camera is 10 frames per second, and we'll see that this process is not firing at 10 frames per second. It's more like 2 frames per second. So definitely not a real-time operation, but still fun and informative. So this is where we're using the generators again. So this is where this is why this is clever here, because what I'm doing is in each iteration of the for loop, we're going to set image left to whatever image plus 1 used to be. And so in this case, before the for loop starts, image plus 1 is the first left image. And so the first time this for loop goes through, image left will become the first image, and then image plus 1 will become the next left image. so that we always have, we're using one generator, but conveniently storing these variables in the sequence that we want them to be in. And then we'll also grab our image right is the next handler.images right. And so now we have the 3 images that we need to do this process with. And so if handler.lowMemory is not true, meaning that all of these images are held in memory, then all we need to do is just say image left is equal to handler.images left for the index that we're on. Image plus 1 is equal to images left index plus 1, go figure, and image right equals handler.images right of the index that we're on. So cool beans, we got that. Okay, so now we need our depth. This is misspelled. A little spell check real quick. Okay. Yeah, so we need our depth map, so we'll go ahead and just grab stereo to depth, and we pass in image left. We pass in image right. We tell the first projection matrix is handler.po. Need a comma there. This is another function that we made in previous videos. I'm assuming nobody that's watching this video is watching it without having watched the previous videos, but you never know. And matcher is stereo matcher, which is whatever we passed into our big wrapper function up here. In this case, it'll default to SGBM, which is slightly slower but more accurate. And since neither one of them are going to operate in real time, who cares? We're going for results here. Okay, so next is our LiDAR correction. Well, it's not a correction stub. Don't let me use bad lingo here. What we're going to say is if we have LiDAR information, we're going to supersede any stereo depth with our LiDAR depth, because even though LiDARs also have noise, most likely whatever LiDAR reading you have is going to be better than any stereo disparity depth estimate. I talked about that already, but if handler.lowMemory, we're going to grab a point cloud from our point cloud generator, point clouds, and if not, then we're going to take a point cloud by its index from the point clouds by the index. And then we'll say LiDAR depth equals point cloud to image. And this is another thing where it's like, you know, this will actually burn up some time on each frame. But we made this function before in that one video. I guess maybe I shouldn't include this because technically I called that video point 3.5, part 3.5, but you know, we're just gonna run with it. So we'll pass in point cloud. If you're really, you know, if you didn't follow that video and you don't have the point cloud to image function, just set your handler.lidar equals false before you start this loop, or else you'll hit an error. So equals in height, in width equals in width TR, which is the transformation matrix between the LiDAR and the left camera, is attached to the handler class, and PO again is also attached to the handler class. And that's not going to work. There. And then indices equals np.where LiDAR depth is less than 3000. because we set before in this point cloud to image function that anywhere where we didn't have LiDAR points, we set the range to the same maximum that the stereo depth does, so that we know where our missing data is. And so basically this function np.where will give us only the indices where we have good LiDAR data. So wherever points from the point cloud got projected onto the image plane into actual pixel coordinates, we will get a list of those pixel coordinates where we have LiDAR data using np.where here. And then the depth of indices, oh, right, so this is our stereo depth that we just created up here. And all we're doing is indexing it with the indices for where we have LiDAR depth info, and we're just superseding our stereo depth estimations with the LiDAR depth. And like I said, if this isn't something you want to happen in your loop, then just before we start this loop, set handler.lidar equals false, and then this will not trigger. And you wouldn't even have to write it in anyways. So that's that. So now we need to extract our features from the left camera and in image left, and the left camera in image +1. So we'll say get key points and descriptors for left camera image of 2 sequential frames. And so KP0 and descriptors 0 will be extract features, a function that we made, image left, detector, mask, and KP1, descriptors 1 will be, again, extract features from image +1 using the detector of choice and our mask if we have one. And that's that. So let's scroll down a bit here. All right, so now we have our key points and descriptors. We need to do our matches. So get matches between features detected into subsequent frames. And we'll say matches unfiltered is match features, a function that we wrote, descriptor 0, descriptors 1, matching equals the matching type that we're using, detector equals the detector that we're using, and sort equals true, which we don't really need that at all. As a matter of fact, I'm just going to leave that out. Don't worry about that. It's complete rubbish. It's just an artifact of me being just doing stuff that I have yet to edit out. Okay, so, and then we need to filter these matches based on our ratio test using our filter matches distance. So filter matches if a distance threshold is provided by user, and we're going to say if filter match distance is not none, then we'll say matches equals filter matches. That's probably could have made this variable a little different in name than this function. The only difference is that this is matches distance and this is filter match distance. It's a little confusing now that I'm looking at it, but they are different, so it's not gonna get in the way. Just be wary as you're following along that this is a function and that this is a parameter that we've passed into the function we're working on right now. Just keep that in mind so that you aren't confused if you get errors. Okay, so we've done each step of the process per frame here. We've started the timer. We've got the images that we need. We've got a depth. We've superseded LiDAR depth if we have it. We have got our key points and descriptors for the image left and the image +1. We have matched the features using, in this case, SIFT and brute force. We're going ahead and doing a ratio test, which I don't know why you wouldn't, but I wrote this functionality in there just in case for whatever crazy reason you've decided not to use the low ratio test on your features. I don't know why you wouldn't. You should. You absolutely should. So this should never happen, pretty much. But it's there just in case, you know, you're feeling whimsical and you want to do things a crazy way. Okay, so now we get to use our estimate motion function, which is what we made in the last video. And we'll go ahead and get our rotation matrix, translation vector, image 1 points, and image 2 points equals estimate motion. And we're going to pass in our matches, pass in key point 0, key points 1, the intrinsic matrix of the left camera, and our depth map. And that will give us what we need. So now that we have those things, we're going to create a blank homogeneous transformation matrix. And the reason I'm doing this, you could also stack a row of 3 zeros and a 1 on the bottom of your 3x4 transformation matrix to do the same thing. But to me, it makes more sense in my mind to take a 4x4 identity matrix and then plug in the first 3 rows as being the transformation matrix that we have here, because right now we have it separated into a 3x3 rotation matrix and a 3x1 transformation vector. So what I'm doing is I'm making a 4x4 identity matrix, and then we're going to say that the first 3 rows and the first 3 columns of that homogeneous transformation matrix will be RMAT, and that the first 3 rows and final column will be the TVEC, and we need to transpose that. But this just seems cleaner to me. So, and remember, the reason we're doing this is because we need to invert it. And so you can only invert a square matrix. So we can't invert a 3x4 matrix. So we make it into a 4x4 matrix that is a homogeneous transformation matrix, and then we can invert it to reverse the transformation. So yeah, so there we have it. Okay, so here is the interesting part that tripped me up the first time I did this, is that what we're going to do is keep track of a variable called t total, and whatever t total was before is going to get dotted with the inverse of this homogeneous transformation matrix that we just did. So what do I mean by that? What does that mean? So it turns out that if you dot 2 transformation matrices together, that it combines the transformations of those matrices. So 2 homogeneous transformation matrices dotted together will give you the combined transformation of those 2 matrices. And so up here, I made T total into a 4x4 identity matrix because in the first frame, uh, the camera hasn't moved. So the transformation matrix of the very starting frame is an identity matrix. And then we set the first trajectory, so the trajectory at index 0, I took the first 3 rows of that 4x4 identity matrix and stored it in there because that is the first trajectory pose is an identity matrix, except it's a 3x4 because that's the way we're storing them, not as homogeneous. So in this line, think about the first time this for loop goes through. T total is an identity matrix. So when it gets dotted with the inverse of T mat that we just made, the result is going to just be the inverse of T mat. Now, what is the inverse of T mat? The inverse of T mat is going to represent the transformation that you would need to perform on the origin of the first position of the camera to turn it into the origin of the camera in its second position. So that means that whatever the translation vector of the inverse of TMAT is, represents the 3D coordinate of the origin of the camera in its second position in the global coordinate frame, which is the coordinate frame of the camera in its first position. We're inverting it because when we get TMAT here, what it is actually telling us is how you would transform the coordinate frame of the camera where it is now, meaning the second position. How would you transform that coordinate frame to get it back to where it started, which means that its translation vector would be, say, okay, so in this case, the car is moving forward in the beginning of this sequence. So if you want to know where the origin of the camera is in relation to its coordinate frame in the first frame, then it's going to have a positive z value because it went down the z-axis. Now, when we get TMAT here, if you were to inspect it, which let's go back up here because I already have it out. This we used our estimate motion function here, and it made RMAT and TVEC, and then I stacked them together and we looked at it, and you can see that the z value here is negative because these 3 numbers are telling you where the coordinate of where the origin of the camera in its last frame is with respect to where it is now. And that's the opposite of what we want to know over time. We want to know where the origin of the camera is now with respect to the coordinate frame of where it started. So that's why we're inverting this matrix, is that we want to flip this around. And when we do that, down here I made it into a homogeneous transformation matrix, just like I'm doing in the function that we're making now. And when I invert it here, you see that this z value is equal, but it becomes positive. Okay, and so this is why we're inverting it, because we want to know where the camera is with respect to its last coordinate frame. Good. Now, this is going to accumulate over time, and so T total now is the inverse of TMAT, which is where the camera's origin is with respect to its original coordinate frame. And so the next time this loop comes around, we're going to get a new TMAT, and that TMAT is going to be describing where the origin of the camera was in the last frame with respect to where it is in the third frame, which is something we don't really care about at all in the end, because we want to know where the origin of the camera is in the third frame with respect to the origin of the camera 2 frames ago where it started. But so what we're going to have is that we're going to invert it first, which will tell us where the origin of the camera in the third frame is with respect to the coordinate frame of the camera in the second frame. And then we're going to dot it with the transformation up to that point from the where it started from, which, as I told you, when you dot two homogeneous transformation matrices together, you combine them. So then we will have combined the transformation from the start to the second frame with the transformation from the second frame to the third frame. And so the result will be the transformation from the starting frame to the third frame, which is what we want. Because as we do this in every frame, the t total that we get will represent the total transformation from the camera's starting coordinate frame to the coordinate frame where it is now, which will allow us to draw our trajectory with respect to a single coordinate frame, which is the coordinate frame of the camera when it started. So that's sort of complicated, so rewind this back, play it back, listen to me explain that a few times. But that is what is happening, is that we're solving for, I mean, really you could just rewind me saying it, but I'll reiterate one more time just to make it clear. We're solving for the change in pose of the camera from whatever the last frame is to the frame we're thinking of now, and that we want to reverse that to know where the origin of the camera is with respect to the last frame we were dealing with, and then we're going to multiply that with where the camera is in that last frame we're dealing with regards to the origin that we started from, to combine them to get the idea of the total transformation of where the camera is now in comparison to where it started from. And that's what is happening here. And so once we have t total, then all we have to do is stash it in our trajectory in I plus 1, because in this case we're solving for the position of the camera in the image plus 1 frame, which is why we're doing this for loop in a range that only goes to number of frames minus 1, because we're actually solving for the last frame here, because whatever frame we're solving for is the frame where image plus 1 is. So in this case, that's why when we store our trajectory, we're saying index plus 1, because that's really the frame that we're solving for. And we're going to say all rows and all columns, because again, this is a 3x4 transformation matrix that we're saving it as. And so we're going to say t total the first 3 rows, because we don't care about that last homogeneous row. It's only there for mathematical convenience, and all columns. And so now we have saved our total transformation up until this point in our total trajectory, which is what we'll be returning in the end. And we've gone ahead and just taken the first 3 rows of that. And t total will remain a useful thing to incrementally dot with the next inverted tmat that we get in the next frame, which is, that's it. I mean, this is it. So now we can end the timer. Datetime.datetime.now. And we'll go ahead and tell the user time to compute frame, and so frame blank, and we'll say format I plus 1 to tell it which frame we just computed the pose for, and then we'll say n minus start. And so that'll be it. And then if plot, again, we're in a little, in case we're doing our fun interactive plot, then we're going to get the x's up until now from our trajectory, the y's and trajectory up until I plus 2. Now, why is it I plus 2? Well, it's because when you're indexing in NumPy, it's not actually going to get I plus 2. It's only going to go up to I plus 1, which is the index that we just modified. So we have to say I plus 2. And then z's equals trajectory up to I plus 2 again. Oops, I plus 2, 2, 3. And then go ahead and say plt.plot x's, y's, z's, and the color will be chartreuse because I like it. And then plt.pause, and we'll say 1e to the negative 32 because we don't want it to pause at all, essentially. And then so that'll happen every frame. And then we get out of the for loop, and then I'm going to say if plot again because after the for loop is over, we want to say plt.close. Oops, because that'll close the window, and that's only necessary if we've been plotting. And then in the end, we're returning our trajectory. So that should be it. Assuming that I wrote that without any typos, that is our visual odometry function. And so this is an exciting moment for us. It's been a long journey, lots of babbling and completely in-depth discussion about what's going on here. But I really hope that everybody has learned a lot. Oh look, oh, I didn't put an equal sign. If that's all we got to worry about, then we'll be pretty well off. Nope, I forgot a comma. So far, cakewalk. Okay, so it seems to be working. Okay, so this will be a good time to, okay, let's call it trajectory test, and we'll go ahead and I think we can just run this. We pass a handler, all of, okay. So handler, we'll say visual odometry, and then pass in the handler. Is that what it's called right now? Yeah, okay. And for the most part, all of these parameters can keep their default values, but let's just be explicit for the sake of argument here and say we're going to use sift. We're going to match with brute force. We're going to filter match distance. We decided on 0.3, not negative, 0.3. It's a nice harsh distance ratio threshold. I talked about it before. We're going to use SGBM. We're going to pass the mask that we have already made up in this notebook, which I have actually included in the repository. At first I said I wasn't going to, but then I changed my mind. And for this subset, let's just do 50 frames. To make sure it's working, and so it won't go on forever. And then we'll say plot equals true. And so I'm going to go ahead and switch us to full screen so that we can see the plot and everything. Let me close all of my windows that I had open. So, okay, so let's full screen this baby. That's right, I listened to, I don't think it's, oh, it is full screen, okay. Good, good. All right, so let's see if this works. Fire away. Okay. Well, looks like we've hit an error. got a problem here, and the problem is we don't have enough points in the solve PNP ransack, so somehow we've managed to not provide enough points. The count is fine. Okay, so what this is telling us is that we don't have enough features using our distance threshold of 0.3. We've filtered out so many feature matches that we didn't have at least 6, which is, I mean, there should have been enough, but let me just make sure that this is working. You know, because it says we're doing stereo SGBM, detecting with SIFT. Well, let's go with 0.5, just because, I mean, essentially that's what has happened, is that using this 0.3 distance ratio, we have over filtered to the point where we didn't even have enough feature matches between these two frames to even use solve PNP ransack, because it needed at least 6 and we only gave it 5. So clearly in this go around we're going to not be able to use 0.3, even though I used it before, but this runs a little differently every time you do it, so we'll try again. Yeah, so we can see our trajectory starting here. It's growing very slow. Oh, we hit another error. Okay, something's wrong here, because this should not be happening with a 0.5. So, time for a little debugging, folks. Time to do a little debugging. So I can't lead you all this way and then give you something that doesn't work and then be like, oh yeah, just look at the way it's done in the main notebook because it works there. Clearly. So okay, we have matches. Filter match distance is not none. We're just doing matches unfilled, which we're making here using descriptors 0 and descriptors 1. We are making those here. We have image left, detector mask. So okay. So somehow we are, let's add some print statements here for a sanity check. We're going to say number of features before filtering, and then we're going to say length of matches unfilled, and then we're going to take this line and then put it down here and change this to matches and change this to after. And I'm going to add a cell here that says plt.close, so get rid of that. And yeah, let's run this again. So it's going to kind of get in my way here. All right. So we'll hit that error again and it'll stop. Okay. So, yep, as I expected, that doesn't make any sense because you need at least 6 points for pose estimation, and there are 802 matches. So it's not the distance threshold. There's something else going on here, because we're estimating motion using KP1, KP0 and KP1. And so maybe we need to figure out debugging with print statements here. Length of KP0, length of KP0, print length of KP1, length of KP1. Do it again. It should be the same as the number of features that it gets. Should have known I wouldn't get off that easy. I literally do not know why it's doing this. So yeah, KP0 and KP1 are plenty long enough, but it's telling us that it isn't getting enough. So, and this is happening after, so what is happening up here in our estimate motion function? We're getting a list of matches, which is clearly long enough. We're getting KP1 and KP2, which are definitely long enough. We've printed it out. We've made sure that there's definitely more than 6 there. We're getting image 1 points and image 2 points by taking the indexes, object points, and then delete. Okay. So earlier we were using this point cloud to image, and what did I set? So this could possibly be a thing, is that the render, I'm making all zeros, and then I am not setting them. I think that there might be a problem here where yeah, because down here we said where LiDAR is less than 3000, whereas I've never up here I'm not setting anything to above 3000, so it's probably filling up our depth map with a bunch of zeros, which is probably causing an issue. So let me look in this notebook real quick. I knew I shouldn't put that damn LiDAR thing in there, but it's all right. We'll figure it out. Yep, here it is. It's right here. This is not in the function in this notebook because I'm making a render of all zeros, and I didn't include this, which really, when I'm thinking about it, it would make more sense, instead of doing it like that, to just say whenever the LiDAR depth rather than is less than 3000, let's just say whenever it's greater than 0, because it's never going to be 0 with a real reading. So let's do it like that. And let's also comment out these print statements because we don't need them anymore. I'll erase them later. And so this should be working now. Close this. And we'll set this back to 0.3 since it should work now that we've cleared up our issue. Okay. It's like we might be in business, folks. Yep, we're growing. Got our little trajectory here. It's growing. We'll be doing this for 50 frames, but you know, for visual pleasure, here's our, you know, and you know, think this chartreuse line represents our estimated trajectory, and the black line was our ground truth. And as you can see, after 50 frames, we were still pretty close. So, this is working for the most part. But as I, went into a lot in the beginning of this video, the errors that we are producing in each frame will be accumulating with time. And so over time, it's going to drift. So it's not going to be perfect, but we've got it working. I mean, that's it. So this is it. Obviously, I did a subset of 50 frames. So what I'm going to do is go ahead and set this back to none, and I'll stick with you for just a little while longer, because what I'm going to do is I'm going to run this, and then we'll watch it for just a second, and then I'm going to end the video, and then later I'm going to save the trajectory that it produces for posterity, and we'll look at a graph of it. I'll make a short video next week, maybe like Monday after the weekend's over, and yeah, and we'll take a look at the results that we got. But this is it. This is a celebration, everybody. We made it through this whole thing. I think this video is probably long, just like all the other ones. Let me see if I can get it to tell me. This plot's gonna keep popping into my face, so I can't tell easily. Oh yeah, hour and 21 minutes. I thought it was gonna be a short one. So yeah, I mean, this is it. We've walked all the way through. You guys have now seen how this works, and like I said, it's not perfect. There's a lot of ways to improve this kind of pipeline, but really this is the fundamentals of visual odometry. We've done it. So the error is a lot to do with the fact that we're using stereo depth. And so there are other ways to do depth nowadays that are more contemporary. For instance, there's monocular depth estimation that people do with neural networks, which of course, in that case, you would need a trained neural network that was able to use data that was coming from whatever camera you're using. And I don't have a lot of experience using monocular depth neural network inference. I don't know how well one model generalizes to, different cameras or anything like that. But so the thing is that the more accurate your depth, the less error you're going to have, because the whole thing that we've done is very much depending on the quality of our depth estimate. And so we've used a stock OpenCV function, and like I said, you can adjust some of those parameters and see if the error per frame is reduced, and all of that. And like I said, Kalman filtering using the likelihood of the LiDAR scans given the proposed trajectory would be another good, I mean, that's literally the next thing that I would think. And I mean, there's literature on this that I've been meaning to get to myself, but I've got a lot of things I need to be reading. But anyways, we can see ourselves snaking along here, and we're a little off, but I mean, we've made it around 2 corners now, and we're drifting a bit now, but for the most part, we're on. And considering that we're not correcting in any way, this is pretty impressive. We've gone around 2 corners and we're almost spot on, and we're doing nothing but estimating the motion between one frame and the next frame, and then just adding all that together. So it's a fairly naive approach, and obviously it isn't simple, but this is the foundation which your further research will be able to improve upon, because this is the essentials. And so I'm going to go ahead and end the video here because we made it, and next week I'll go ahead and post some results and we'll maybe talk about it a little bit. But yeah, that was fun. I'm glad, glad y'all stuck with me through it, and I hope you learned something. So until next time, see you later.